Professor Dr. Benedict Lemaître, Dean of the Faculty of Theology and Religious Studies, Katholieke Universiteit Leuven. Professor Dr. Christoffel Waelkens, Institute of Astronomy, our keynote speaker, and his wife Mia. Professor Dr. Jan Hovaerts from Universiteit Katholieke de Leuven and his wife Christine. Dr. Jeff Ongena, Research Director at the Royal Belgian Military Academy, and his wife Christel. Respected colleagues and students of the Faculty of Theology and Philosophy and other faculties represented here. Dear students and staff members of Holy Spirit College, and I would like to welcome especially Professor Dr. Roger Burggraven and Mr. Peter de Geiter. Ladies and gentlemen, it is a great pleasure to welcome you all to Holy Spirit College tonight for the second annual Lemaître lecture on faith and science, which our college is organizing in close cooperation with the Faculty of Theology and Religious Studies in our university. This college, where Professor Dr. Georges Lemaître lived and worked, where he developed his scientific theories and lived his Christian faith, is the appropriate place to commemorate his legacy and to continue to meet the challenges that the relationship between faith and science continue to present to us. The fact that so many of you have come here tonight is a strong witness to the fact that the universe and the related questions of its beginning and history continue to fill us with wonder and curiosity. The fact that we are here tonight is due to the generous support of so many. And I would first like to mention Honorary Rector Professor Dr. Mark Verwenne. I would like to mention Professor Dr. Benedict Lemaître, the Dean of the Faculty of Theology and Religious Studies. Our Holy Spirit College staff, especially Professor Roger Burggraven, our Spiritual Director, and Mr. Peter de Geiter, our Director. They believed in this project from the very beginning. Without their support, it could have never seen the light of day. As you know, our evening will consist of two parts. First, Honorary Rector Professor Dr. Mark Verwenne will address us, situating the initiative of the Lemaître Lectures and introducing us to Professor Georges Lemaître under the title Remembering Professor Dr. Georges Lemaître. He will also introduce our main speaker. Now it is possible that you have looked around and not seen Professor Dr. Mark Verwenne. He will speak to us through a recorded message because due to a conflict of planning, he is not able to be here in person tonight, but he has assured me several times this week already in writing that I should greet you very cordially from him and that he regrets that he cannot be here in person tonight. And the second part, of course, will be the keynote lecture entitled Science and Religion, Two Endless Paths of Wonder and Curiosity by Professor Dr. Christoffel Waelkens. And so now we will hope and pray that the technology that we tried out so much this morning will work and that we can listen to the message of Professor Verwenne.
Mevrouw de decaan, beste Benedict, meneer de president van het Heilige Geest College, beste Raimund, professor en mevrouw Waelkens, beste Christoffel en Mia, dear colleagues and students, ladies and gentlemen. It is a great honor and pleasure for me to introduce this second edition of the Holy Spirit College Lemaître Lectures on Faith and Science. Allow me also to welcome two of our guests, Professor Jan Hovaerts from our sister university, UC Leuven, and Dr. Jeff Ongena, Research Director at the Royal Belgian Military Academy. They are good colleagues and friends of both Professor Waelkens and myself, and for me it was a great pleasure and very inspiring to collaborate with them in the past years on the commemoration of Monseigneur Georges Lemaître. Chers Yann et Christine, je suis très heureux que vous êtes parmi nous ce soir. Merci d'être venus. Beste Jeff en Christel, het doet enorm veel plezier dat u vanavond aanwezig bent. Ladies and gentlemen, why is Professor Georges Lemaître at the heart of these lectures? And why in the Holy Spirit College? And finally, why this specific theme? Georges Lemaître was a pioneering Leuven scholar in the field of cosmology. He is part of the common intellectual heritage of UC Leuven and KU Leuven, with at its center the archives Georges Lemaître that are safeguarded and disclosed by our sister university at Leuven. The Holy Spirit College is a particular place when we talk about Lemaître, because he lives and worked here from 1927 to 1933. And finally, the theme Faith and Science. Lemaître was a priest and a physicist. He was very conscious of the tense relationship between Christian faith, proclaiming the world as created by God on the one hand, and the scientific theory of a universe formed approximately more than 10 billion years ago. This explains our choice for faith and science as the key theme of the Holy Spirit College Lemaître lectures. In 2023, we started with the first lecture, and this lecture was pronounced by Professor Leen de Sen from KU Leuven. The title of her lecture was Hidden Even in the Beginning of the Universe. This year, we have invited Professor Christoffel Waelkens, and he will speak on the science and religion, two endless paths of wonder and curiosity. Allow me first to say something on Monseigneur Lemaître's life and academic work. Georges Lemaître was born in Charleroi in 1894, and he passed away in Leuven on 20 June 1966. He is buried on the cemetery of Marcinelle in his native region in the Pays Noir, the coal mining area around Charleroi. Lemaître was priest, theoretical physicist, mathematician, astronomer. From 1925 until 1964, he was a professor in the Francophone section of the then yet undivided Catholic University of Leuven. After a classical education at the Jesuit College in Charleroi, the young Georges began studying civil engineering at the Catholic University of Leuven at the age of 17. In 1914, he interrupted his studies to serve as an artillery officer in the Belgian army for the duration of the Great War. After the war, Georges Lemaître studied physics and mathematics and began his formation for the diocesan priesthood. He obtained a doctoral degree at the University of Leuven in 1920 and was ordained a priest in 1923 by Cardinal Désiré Joseph Mercier. From the beginning of his academic career, Lemaître was internationally oriented. In 1923, he became a research associate in the astronomy at Cambridge University, and there he worked with Archer Eddington, a physicist and pious Quaker, who introduced him to modern cosmology, stellar astronomy, and numerical analysis. Lemaître spent the next year at Harvard College Observatory in Cambridge, Massachusetts, and at the MIT, which is very well known, where he registered for the PhD program in sciences, the second doctoral degree that he obtained in 1931. In these years, Lemaître and Einstein met several times. In 1927, in Brussels, at the famous Solvay conference. In 1932, on a cycle of conferences in Brussels, in California in 1933, in 1935 at Princeton. Moreover, Einstein and Lemaître corresponded with one another on their scholarly ideas and hypotheses. In this respect, it is interesting to note that Einstein, while not taking exception to the mathematics of Lemaître's theory, refused to accept that the universe was expanding from a primeval atom, because Einstein was afraid that this theory would end up in postulating creation in a religious sense. Lemaître, who was a humorist, recalled his commenting by saying, "Vos calculs sont corrects, mais votre physique est abominable. Your calculations are correct, but your physics is atrocious." Today, Georges Lemaître is acknowledged throughout the world as a truly visionary architect of modern cosmology and the founder of the so-called Big Bang theory. No doubt, he was one of the greatest physicists of the 20th century, who made original contributions in understanding the origins of the cosmos. Lemaître, in fact, was the first theoretical cosmologist ever nominated in 1954 for the Nobel Prize in Physics for his prediction of the expanding universe. He was also nominated for the 1956 Nobel Prize in Chemistry for his primeval atom theory. In 1934, he received the Franqui Prize, the highest Belgian scientific distinction, the Belgian Nobel Prize. Among his proposers were Albert Einstein, and one of the members of the internationalist jury was the Cambridge mentor of Lemaître, Arthur Eddington. Georges Lemaître lived and worked, as I already said, in the Holy Spirit College in Leuven from 1927 to 1933. He also had an office in the Premonstrate College across the Holy Spirit College, very close here in the Naamsestraat. It was during this period that he laid the foundations of his theory of the universe, often referred to as the Big Bang theory. This theory was constructed within the framework of Albert Einstein's theory of gravitation, known as general relativity. Lemaître developed his theory in two stages. The first, in 1927, put forward the idea that the universe was expanding. The second, in 1931 and 1933, hypothesized the so-called primeval atom, proposing the sudden emergence of time and space out of a singular and intrinsically quantum physical state. And that unique moment that knew not yesterday, Lemaître said, cet instant unique qu'il n'y avait pas d'hier. Professor Waelkens, our today's speaker, will certainly develop these insights in more detail in his lecture that we'll launch in a moment. I would also like to refer to commemorating moments that UC Leuven and KU Leuven celebrated together. In 2016, we commemorated the 50th year after Monsieur Lemaître passed away in Leuven, and we did so by establishing two statues collecting both academic biotopes of Lemaître, Leuven premonstrate and Leuven on the Place Georges Lemaître. The renewed public interest in Lemaître, his modest person and high-impact scholarly work could not better be put at the center of interest. And I would also like to say that today, the current bearers of Lemaître's scientific heritage at our sister universities are Jan Waelkens, who is in our midst, the Archive Georges Lemaître at UC Leuven, Leuven en Leuven, Professor Christoffel Waelkens, Leen de Sain, Thomas Hertog at KU Leuven. In 2019, the European Physical Society has recognized the Holy Spirit College in Leuven as the EPS historic site under the impulse of Dr. Jeff Ongenaar in our midst and Professor Jon Govaerts, who is also with us. At that moment, we also introduced the Big Bang route between Leuven en Leuven and Leuven with the support of the two provinces and the two cities. Finally, in 2021, we organized the Leuven City Festival now, with a great exhibition at the Museum M, the Imagination of the Universe, and an exhibition at the University Library with, as its curator, Professor Thomas Hertog, Beyond the Big Bang, in close cooperation with the Archive Georges Lemaître of our sister university. Ladies and gentlemen, Georges Lemaître's life was driven in search of truths, both as a scientist and a religious person and priest. From 1934 until his death, he was a member of the Pontifical Academy of Sciences, to which, during his presidency from 1960 to 1966, he brought a visionary openness of spirit. It is quite clear that Lemaître preserved all his life the mystery of a supreme and inaccessible God, enabling him to keep the natural origin of the world within the strict limits of physics, without mixing it with supernatural creation. Lemaître was very conscious of the potential conflict, or should we say, of the complementarity between the Christian belief of a world created by God and the scientific claim of a universe formed more than 10 billion years ago. However, he never confused science and religion. He was very cautious not to use one of these two ways of knowledge, as he called these, as a legitimation of the other. He carefully distinguished between the beginning and the creation of the world, and never spoke about the initial state of the universe in terms of creation. Lemaître was convinced that science and faith, including theology, develop a different but complementary discourse. Both start from curiosity and fascination, but then go their own ways. Cosmology and physics apply the methodology of the natural sciences, whereas theology and biblical studies rely on philosophy, anthropology, linguistics, literary studies. Natural sciences go by observation and interpretation of facts. Theology and biblical sciences and faith as well go by the metaphorical dimensions of religious texts. Professor Waelkens will also focus in detail on this nuanced approach to the relationship between science and faith. Lemaître confined himself to physics, mathematics, cosmology. And during the Second Vatican Council from 1962 to 1965, he was invited by the then Pope John XXIII to serve on the fourth session of the Pontifical Commission on Birth Control. However, he definitely did not accept this invitation, expressing surprise that he was selected. He said that, according to him, it was dangerous for a mathematician to venture outside of his area of expertise. For the 2024 Holy Spirit College Lemaître lecture, we have invited an eminent specialist who is an éminence grise in the field of cosmology and also closely related to the life and work of Monsieur Lemaître. Emeritus Professor Christoffel Waelkens of KU Leuven is an expert in stellar structure, stellar evolution, and space research. His emphasis is on the interpretation of modern observational data of stars and their environments, obtained with new observatories on the ground and in space. He represented Belgium in major committees of the European Southern Observatory ESO and European Space Agency ESA. He was chair of the Leuven Institute for Astronomy. In his lecture entitled Science and Religion, Two Endless Paths of Wonder and Curiosity, Professor Waelkens will focus on the complementarity of science and faith as related to the person and the scholarly work of the late Louvain professor Monsieur Georges Lemaître. Professor Waelkens argues that Lemaître has thoroughly dealt with both science and faith, which he saw as two different paths to the truth. According to Lemaître, and I quote, "The conflict between science and religion has always been between those who fail to understand the true scope of either science or religion." End of quote. In cosmology, he showed the right track to pursue our scientific journey and anticipated that it is a long one. The fascination for the universe continues to inspire our curiosity. The lecture of Professor Waelkens is an attempt to assess where we are now on the endless path of cosmological research, and also to express how there is still no conflict today. Ladies and gentlemen, dear audience, on behalf of the organizing committee of the Holy Spirit College Lemaître lecture, I would like to thank Professor Waelkens for having accepted our invitation to deliver the Lemaître lecture 2024. I do once more apologize for not being part of the audience tonight, what I would have left, since I know Christoffel as a brilliant and inspiring scholar who always enthuses his students and audiences and opens new avenues to think about science and religion in an open mind and in a spirit of dialogue. Finally, I would also like to express my gratitude to Professor Raymond Bieringer, President of the Holy Spirit College, for having taken the initiative to set up the Holy Spirit Lemaître lectures on science and faith. In addition, I recognize the services of Professor Roger Burggraven, Spiritual Director of the College, and Mr. Pieter de Geiter, Director, both members of the organizing committee of the Holy Spirit College Lemaître lectures. No doubt that these lectures are a forum of debate and dialogue, which is part of the mission of a true Catholic university that is a place of conversation. It is time to give the floor to Professor Christoffel Waelkens, who is an excellent guide for understanding the scholarly work and the person of Monsignor Georges Lemaître in relation to cosmology and religion. I wish all of you an inspiring conference. Let now arouse your curiosity. Thank you for your very kind attention.
Good evening, everybody, and thank you very much. Thank you very much for being here, and I thank the organizers for inviting me. And there we are. It's a big honor for me to be able to talk to you about a subject which I like very much. I am not really an expert in cosmology, but cosmology is the background of everything regarding the universe, so this is the basis of all our work. So if you are an astronomer and have no clue to cosmology, well, I mean, then I don't know what you really think you are. We are the science of everything, and the whole background is cosmology. So I will venture to talk about some things in which I am not a specialist, and I'm afraid that Mark Vervenne said that Lemaître wouldn't accept that. So, okay. Well, I'm very happy that it is in the presence of very good friends who were important in bringing to the attention of the broader public the very important contributions of Lemaître, and to honor him partly by this plaque which we have here in front of the college. I can see it from here. Yeah, the lights are on there. And so there is one slide I have not put on, and because you can look it up there. Good. So let us start with Lemaître. As he was telling in 1933, on the front page of the New York Times. For every scientist, well, publishing in Nature is important, and in Science is important, but being on the front page of the New York Times is still much more important, of course. Well, and he was asked, of course, as a priest who really had brought a revolution in cosmology, how things went together. And then he said this famous phrase, that the real cause of conflict between science and religion is to be found in man and not in the Bible or the finding of physicists. When men were told that they had the right to interpret the Bible's teaching according to their own lines, he holds, naturally some were bound to decide that its science was infallible, and others that it did not agree with modern instrumental measurements and was a proof of opposite doctrine. So he was a very classical religious scholar in a sense, not accepting too strange interpretations. The conflict has always been between those who fail to understand the true scope of either science or religion. For those who understand both, the conflict is simply about descriptions of what goes on in other people's minds. It's a very nice phrase to really, well, respect the independence between both. Of course, science, well, cosmology is about everything. Religion is also about everything. There's only one everything. And so these two pictures, well, there must be some consonance, and that is up to everybody to find out. And that is what the lecture will be about today. But, well, I mean, a cosmologist who does not believe can be a very good cosmologist. I mean, and some of them are, obviously. I mean, it's obvious to go into to solve equations and to try to interpret them is a purely scientific matter. On the other hand, I am a citizen of the village of Tremelo, and we have Father Damien, who was born there, and he has been sanctified by the Pope even without knowing anything about cosmology, and I think he deserved it. So it's independent, but, well, it is still, one cannot be schizophrenic, and that is what I will in fact develop. But first, and to stop here, I have to explain a few words about the Big Bang, about the science work of Lemaître, and we will introduce the other things later on. That is the most, well, the view graph with most words. But we will, that and the next one we will spend some time on, because it's important to have to understand that. What does it mean, the Big Bang cosmology? Well, it means that the universe evolves as a whole and its components. And this evolution has had a beginning when our time and space originated. These are heavy words. Huh? There was no time before, as you heard, well, there was no time before, but there was no before. So if I said there was no time before, I'm saying already something stupid. The beginning of time. Okay, we come back on that. And the theory is based on 4 observational pillars, which I will explain. The expansion of the universe, the evolution of stars and stellar systems, the cosmological background radiation, and the composition of matter. If you hear that, you wonder whether that is fundamental. Huh? Have you ever do you see well, in our daily life, we don't see the universe expanding. Well, some of you, well, I mean, I have already a certain age, and the sun was the same 17 years ago than it is today. So what is this evolution of stars and stellar systems? The cosmological background radiation. Well, that's probably the only thing you have already seen when you have ever used analog television screen, because a few percent of the noise on the television screen is due to the cosmic microwave background radiation. Show to the students, if you watch television, you are doing cosmological observations. So it's nice to, but otherwise, this cosmological background is far from our bed again. And the composition of matter, well, yes, why there is so much hydrogen and so much gold, and why there is more oxygen than there is gold, and so forth. That also is one of the pillars here. So all arguments far from our bed, who doesn't appear to be, well, to be fundamental, but they are. And because, in fact, the problem is our bed. It's too small, and our lifetime, which is too short. But what it is about is, well, the composition of the universe in terms of matter and radiation, and the evolution and the structure, and how matter is structured, how radiation is structured. It's the content of the universe and the structure of the universe. It's indeed these 4 arguments, and that is something which I will have to explain to you. So I know this is full of pictures, and I will need 10 minutes to explain it, but I wanted to have it all in there. Yes, there are 4 arguments. First, the expansion of the universe. The story started with, in fact, Slipher, in the beginning of the 20th century, who was the first really to be able to determine the velocities of galaxies far from us. Oh, I should have started the picture with showing planets, stars, galaxies, and the universe. Huh? So I guess you know that our sun is a star, and our planet is, our Earth is a planet orbiting the sun. In fact, well, it's very strange. We say, we talk about our Earth as about the planet. It's the only object in the universe which is not a planet. In fact, what is a planet? It's an object which is moving between the stars. And for the Greeks, the sun and the moon were also planets, but they move between the so-called fixed stars. Of course, since we know that the fixed stars are not fixed at all, they move as well. And all these galaxies, they are so far, we can hardly see the movement, but at the end they move as well. There's only one object which doesn't move from here because we stand on it, and it's the Earth. Okay, we call it the planet. Very nice. Sorry. And there's stars, and then all stars together from galaxies, and the galaxies are, in a sense, the building blocks of the universe. And you can determine whether a galaxy moves toward us or moves away from us by analyzing the light. And that's the famous Doppler effect. Doppler effect. Is it Doppler effect? We will see. It's the effect you have when you hear a car or a sirene, what is it, a siren approaching you or going away from you, and the tone is higher or lower. So if the galaxies recede from us, their light is reddened. If they approach us, they get bluer. And what Slipher observed is that most galaxies are receding from us. Imagine, everyone is running away from you. That's not a very nice moment to live, huh? So, big depression among astronomers. And, well, who saved us from the depression? Hubble, but in fact, in the first place, Lemaître, with this law you have there. And you see on the first picture, the galaxy is moving away from a central point, so to say, and then there, the Hubble's law, which tells you that, in fact, the farther away the galaxy is, the faster it moves from us. It's a linear law. Well, you have 3 points. I mean, that's, we will see it in more detail later on. And that saved us from the depression. I will tell. Well, in fact, I do not have to venture outside my field, Lemaître would say, but I will become a psychologist for a moment. If you feel that you are really rejected in the world and everyone is against you, one useful thing to do is to put yourself in the situation of someone else and look how the other person behaves, thinks of. So, because if you, well, we have a galaxy, we are here, we have a galaxy moving with a certain velocity, 2 times faster with 2 times the distance, and the same in the other direction. If you go here, if you ask the galaxy here, why are you moving away from me? The answer will be, oh, you are moving away from you. You are moving away from me. Huh? And the other galaxy is also moving from him, but a little bit less fast. Huh? So you just subtract all the vectors, and you realize that he sees exactly the same thing. He sees exactly the same thing. Everyone is running away from him, which means, well, what? Well, that he is as ugly as we are. Huh? So, and then we are nice again. So then we are saved from our depression. So it seems that the whole space is expanding, and that is an important aspect, because it is indeed true, if you put it in the right formalism, which is Einstein's theory of gravitation, we will come back on that later on a little bit, then it's not so much the ambulance who is recedes from us on the motorway. No. We are standing still and the ambulance is, but the road is getting low. It's space itself which is expanding. Okay. That was a very strange observation, but we'll come back later on. It's not that strange. But then the next point is, yeah, okay, well, we will now have a very, very, very difficult reasoning. If the universe is getting larger, yesterday it was smaller. You follow? Yes. It is as simple as that. And in fact, well, we see someone walking away from us 5 kilometers per hour, and he is at 10 kilometers, and someone else walking away from us, he's at 20 kilometers, and he's running 10 per hour. The first one, how long ago was he here? 5 kilometers per hour, 10 kilometers, 2 hours ago. The other one, 20 divided by 2, 10, 2 hours ago. Huh? All of them were together so much time ago. So if we divide a distance by a velocity, we get a time, and that's the time scale since it all started. If from this Hubble-Lemaître law, which is, as it is called now, we would find a time scale of 20 years, you would say, well, that cannot be the beginning of the universe, because 20 years ago I was already here. But you find out it is about, well, at that time it was about 2 billion years in the early days. Now it has grown older, it's 14 billion years now. The measurements have changed, so it's an evolution of better measurements always. So yeah, that fits. Well, it didn't fit exactly with the age of the Earth, which they knew already was 4 billion years. And therefore Lemaître had to find a model which fitted that, and which is a nice aspect of the whole story. Well, he knew that the Earth was older, so, well, this division by distance by a velocity could not really apply, and that's obvious. Let's again look at these people walking. Well, if I say they were here 2 hours ago, that's because I assume that they have walked at constant velocity. But maybe they were jogging and getting tired now, then they were faster in the beginning, and so the time scale is shorter. That would not solve the problem here. But another possibility is that they have had a coffee break and resumed their walk, and then it was longer ago. And so it depends on the history. And what determines the history? Well, the gravitation of the universe. So you would expect that gravitation will slow it down, but here we had a term which made it faster. That was something, in fact, Einstein introduced for totally other reasons, but Lemaître needed it, and then it was finally removed, this term, for quite some time, because people realized our distances are wrong. And well, since the time of the old Greeks, the main issue in astronomy is about determining right distances. And it's obvious, the stars are far from us. It's not obvious to determine the distance. And well, Hubble was a factor 7 wrong, in fact. Okay, but then I come back to this 4 billion years of the Earth. Well, we can rather well from stars have an idea about the age of the universe, and especially from these stars which you see in the picture there, the kind of globular star clusters. Quite some stars together, which obviously have born at the same time. And in this cluster, we know, in this kind of clusters, we know that these stars must be among the oldest in the universe. How do we know that? Well, because stars, you may know a little bit, I will not have a full course of astronomy, but at least a little bit. Stars owe their energy from nuclear fusion. From light elements, they form larger, more massive ones. In fact, the universe starts, we will see it in a second, with only hydrogen and helium, and all the heavier elements have been generated in stars. And at the end of the stars, they get unstable and they explode sometimes, and all these elements are given back to the environment. No, are not given back, are given to the environment. So stars are like people, either. So they are born and they die, and they try to make the world so that their children have a better living than themselves. They enrich the world with more heavy elements. Well, these globular clusters hardly have any heavy elements. So that means that they have had very little ancestors. And then, well, how can we know then how old they are? We know these are among the oldest ones. Well, the point is that the lifetime of a particular star, well, we can determine that. We know what the energy source is, this nuclear fusion. And, but we also know that the more massive a star, much like with cars, they consume more. And massive stars consume a lot more. And that's because the nuclear reactions, well, a massive star has more gravity, so it's hotter in its center, so the nuclear reactions are much more efficient and they produce much more energy. So that means that massive stars do not live long. A star of 10 times the mass of the sun has 10 times more mass to burn, but it has a luminosity which is 5,000 times bigger. So the lifetime is 500 times smaller. So in the globular cluster there, all massive stars are gone. And what finally happens, and that is this figure there, which explains us how to do, but I will not go into that details. It's very simple. So, well, it is here, this point here, is where stars have exhausted her central hydrogen. Stars which are lower have still not. But stars which are higher are gone. Because the more massive the star, the faster it goes. And so, well, it's like, if your car consumes 5 liters per 100 kilometer, and there are 50 liters which go into your tank, you know you can drive for 1,000 kilometers. But how will you know how much there is still in the tank? Well, normally you don't know, you don't see that if you see a star on the road. But if you, on the motorway, you see a star parked there, and 500 meters further you see someone the jerry can going to the fuel station. Yeah, now this one has exhausted, and he has done exactly 1,000 kilometers. So these turn-off stars are the ones which have just exhausted their hydrogen, and we know we can compute how long they have lived. And what do we find? 10, 12 billion years. And with the expansion of the universe, we find something of the order of 14 billion years. So it concords. And that is very important because this is the same time scale, but determined in a totally different way. First time, a distance divided by velocity, and here, the content of a tank confronted with the exhaustion, the combustion of it. And we find the same number. So then you start believing in this Big Bang. That the universe started then, and then that the first generation of stars started a little bit later on. That was so far Lemaître was aware, in a sense. But then, of course, the problem then was that in the early universe, the universe was smaller and smaller and smaller, and at the end, it reduced to a mathematical point. Well, it's hard to reduce everything to a mathematical point. From the moment we know that at the end, the objects we see are composed maybe of point sources at the end, and the objects which have empty space between them, maybe you can get everything together. But the physics of these extremely large densities was unknown then. It still has to be explored, and that happens in these big accelerators we have. And Lemaître, he was not, he was very good in mathematics. He was very good in having a total overview. He was not an expert in nuclear and elementary particle physics, and that was harder. So he used this famous primeval atom, because nuclear fission was then the new thing in town, nuclear fusion and elementary particles. At the time he wrote the paper, the neutron had not yet been observed, so this had to evolve. But the point is that if the universe was very, very dense, it must mean that the atoms were really ionized, so that there could not be neutral atoms between. But if you take a hydrogen atom and you have the central proton as a pinhead, 1 millimeter in diameter, you put it on the central point of a football field, the electron is at the edge. So to bring everything together, you have to break down the bindings, and that means that you need high energies, but then you have matter which is charged, and that means that the light is generated. So we must have had in the early days of the universe a mixture of matter and radiation. And this radiation then, as the universe expands, the radiation also expands, gets colder. That means that the light, which was first very, very hot, so the wavelengths like gamma rays and X-rays move to the UV, the optical, the infrared, and so forth. But it should still be here. You cannot just, so the atoms cannot just absorb all that light, and elementary particles certainly cannot. So the radiation should be there. And of course, there it is, the blue curve. We have there a picture of the kind of picture of the sky, where the equator is our galaxy, and the upper figure is in infrared. And so we can see very well up to the central region of our galaxy. We can look through the dust and so forth. So we can make these kind of pictures in all kind of colors now, from gamma rays to the radio. But at 1 millimeter, and at all these other wavelengths, you see, in X-rays you see all exotic sources, neutron stars, supernovae, go on. In gamma rays you see still more exotic objects. In infrared you see, the cold universe. And this millimeter wave, but always sources, a combination of a lot of sources. Here you have only one source, the universe. And the radiation has exactly a thermal nature. You can determine the background radiation as it is today. You can determine its temperature with a very high accuracy. Good. That was number 3, and that is something Lemaître learned on his, when he was dying, in fact. He was already in the hospital at that time. And, well, that was the final argument for accepting this Big Bang. And it is still today, but today it has become even much more rich. So, the fact that it is homogeneous means that the source is the universe. The fact that it has this very typical temperature spectrum, which I haven't shown here, means that, well, it comes from, it was generated in a time when the universe had a uniform temperature and only afterwards cooled down homogeneously. But if we had this very hot early universe, everything was in thermodynamic equilibrium, one temperature, it works. And then the final thing, now we know the temperature of this. And our theory tells us if the universe was twice smaller, the temperature was twice as high. And then we can reconstruct the thermal history of the whole universe. And we know, for instance, that after about 400,000 years, atoms could finally start to be bound. Before, it was too hot. If a hydrogen proton would join with an electron to form a hydrogen atom, it would have been split immediately by the radiation. But we know also, if you go farther and farther and farther, that if, before 10 seconds, no nuclei could exist. You couldn't have heavy nuclei, because all matter had to be in elementary particles, protons and neutrons. You may be surprised that we know what happens after 10 seconds. The point is that at that time the temperature was, well, some billions of degrees, which we can try to, well, we have an expert in plasma physics here, we can try to create in our nuclear reactors, and the density is still reasonable. After a minute or so, the density of the universe was already as low as 1 kilogram per liter. The universe is empty, you have no idea. Okay. And then, if we bring all this together, we realize that doing the physics there, the outcome of the 3 minutes of possible creation of nuclei was 75% hydrogen, 25 helium, and a little bit less than 25 helium, and no heavier elements. Because the heavier elements, you can make them in stars, because stars during their lifetime, in their course, they form these elements, and during their lifetime, they shrink. Because if they don't produce energy, the gravitation makes them shrinking. But here you have a universe, well, which expands. So it becomes harder and harder to join. And helium being a very stable element, after helium hardly anything happens. So all this together is, well, so with only the expansion of the universe you are on 1 feet, and with the age you are more, and then if you have the 2 others you are on 4 feet, and then you feel very stable. Okay, so that is the longest one. And then the contributions of Lemaître himself. Well, he discovered, in a sense, the expansion of the universe. Yes. As I said, he did not make the measurements himself. He had heard about this redshift from others, but he understood that within Einstein's theory of gravitation. Because he realized that the universe, according to Einstein's theory, must be dynamic. And, well, that is what I wanted to say as well. In fact, on a very large scale, we have 4 interactions, 4 physical interactions in physics. 2 of them are nuclear, they work on very small scales. Then you have electromagnetism. On large scales, they do not really influence that much, because you have, well, the cancellation between positive and negative charges. So the universe is dominated by gravitation. And gravitation is essentially unstable. I mean, well, if you climb into a tree, you know that you have to be careful not to fall. But if you start falling, you fall until you are there. And in fact, take a universe which is totally homogeneous and have a small region where you have a little bit higher density than the surroundings. What will happen? Points on the surface will feel a little bit more attraction towards the center. Your region will shrink. The density will increase. The density contrast will increase. So it will collapse. Stars, galaxies, all start with gravitational collapse. So gravitation is essentially destabilizing. And if a universe based on gravitation can only be a dynamic universe. And that is what Lemaître realized. And, well, I tell to my students, sometimes, you may give a stupid answer sometimes at an exam, but don't think that your career is gone. Because, well, who are the two most famous physicists in history, and also the two fathers of gravitation, Newton and Einstein? Newton, he saw the problem. So he had a kind of stationary universe and it had to collapse. So he made it infinite. And then people told him, well, if you have an infinite universe, every line of sight should encounter a star somewhere. So the brilliance of the universe would be uniform in all directions, typical brilliance of a star. And that's not true. Well, how did he solve that? Not at all. With the method of the tapestry, of the carpet, and he just moved it under the carpet. Einstein, when he realized that his theory of gravity, which was more based on the relativity of space and time, so there was a relation between gravitation and the geometry of the universe. Well, when he realized that it was dynamic, he put an additional term, which was not necessary. So I said to the student, well, look, these two great people in science have said something extremely stupid, and they still are respected. Okay, and they're happy with that. So Lemaître said, well, that must be dynamic. It is in the equations, and it is also at the base of the theory. And then that should mean that we will have this kind of linear law, which Hubble discovered independently afterward, and it was true. And now the law is called the law of Hubble-Lemaître because the International Astronomical Union recognized it. He also was the first, to develop a cosmological model based on observations. Hubble did not understand the theory, and Einstein was not interested in observations. I mean, he was the theoretical physicist who would think and discover the universe totally by himself. Lemaître was combined both and realized that he had a problem, and then he had his model with the cosmological constant, which was then acceptable. He also looked for this background radiation, but in fact not for that background radiation. He realized that the first minutes of the universe must have been extremely violent and that should be still recognizable somewhere. And, well, there is still today very high energy radiation which comes from galaxies and stars, and that's called cosmic radiation. And he thought at the moment that was the remnant of the Big Bang, and he was wrong on that, but he looked for it. And, well, very interesting, he was the first to formulate a hypothesis of a beginning. That if it expands, it was smaller yesterday. He was the one who made this very interesting conclusion. And then later on, well, there are certainly other things. He was the first to discuss the formation of galaxies. So in his universe, with the coffee break, there was a rapid expansion and then a kind of coffee break, and then it went up again. We will see that later on. And during the coffee break, the expansion of the universe was small. And then at that moment, the gravitational collapse could make galaxies. It's true. It's true. But he was the first to develop a theory about that. And then this kind of cosmological constant introduced by Einstein, used in his models by Lemaître, well, if you put it on the other side of the equation, it has a kind of dimension of an energy density. And so he called that the energy density of empty space. And that's exactly what people do today. It's a so-called dark energy. And then finally, and there I have alluded to it, it's the paper in Nature which is there in front of the Institute. He was indeed the first then to have some kind of interpretation of the universe as a quantum, of the Big Bang as a quantum phenomenon. Okay, so he was really a giant. But it's not all solved, and no. So I will talk about some problems which we have today. And here, well, you recognize me here. I was at this conference where this brilliant professor there says, well, after the discovery of antimatter and dark matter, we have recently discovered the existence of doesn't matter, which seems to have absolutely no influence on the universe. So that is the cosmological debate today. Well, what are the new questions? Well, indeed, there seems to be more than we can see. Dark matter, dark energy. What they are is not very well understood. And then, of course, the Big Bang itself is a mystery. And then, well, it is a mystery. It happens at infinite densities. And, well, I said after 10 seconds we can, to some extent, reproduce the situation in our accelerators. But, well, we have no real clue for infinite densities. Infinite is always more than something. And well, okay. When the accelerators at CERN will cost more than the total global product of all countries together, I think we are close to the limit. Yeah. Okay? So, but there is also a theoretical aspect there. Because, well, you may have heard about the physics of the infinitely small, the quantum physics, where you have in the individual particles, but also energy is in a sense, is in different levels, discrete levels. Well, in fact, you are the perfect illustration of quantum physics. I have been teaching for 40 years, more or less, yes, and always in an auditorium where students are sitting on a chair. Always, you put chairs and the students sit on a chair. And you never see two students on the same chair. That is quantum physics. But on the other side, the infinitely large, it's about the geometry of the universe and Einstein's relativity theory. That's a continuous theory. So, well, both Einstein equation and the Schrödinger equation fundamentally explain the same thing. It's conservation of energy. But in a different picture. And to bring them together, well, I mean, there's no problem, as long as the infinite is infinite and the infinitely small is infinitely small, you have no problem. But at the Big Bang, the infinitely large was infinitely small. So we have to unite these two theories, and people really have a hard time finding the theory. So there is a theoretical theory there, and we have done this string theory, and okay, you have a lot of things. And then finally also, not finally, why are the laws of physics what they are? I told we have 4 fundamental interactions, that's what we experience, but why is that? Why is gravity such a strange thing? Why are their relative strengths as they are? No clue. Okay. But that's for theoretical physicists. We astronomers, we are happy with the Big Bang in the sense that we know now that the universe has a history, starting with the Big Bang up to today. And in the Big Bang, you cannot have had structures. At a certain moment, they must have formed. And then, well, so we are, it's like we discovered history on Earth, and we said, well, we have the Neolithic period, and the Bronze time, and the Iron epoch, and then, well, and then the French Revolution, and the Belgian Revolution. Which one was first? I think the French, right? So, well, we start to reconstruct the history, and that's what we do. We try to understand the history. So it's very interesting, but no, I think, well, I don't see, no, because, oh, well, I have, no, I should, Maybe I come back. Do you want me to discuss more of physics, or shall I a little bit go to the other aspect? Well, no, very short. Dark matter. Dark matter. How do we know that there is dark matter? From these kind of pictures. Now, how do we know how do we know the mass of the sun? By knowing how far we are from the sun and how fast we revolve around the sun. Because, well, if we wouldn't move at all, we would fall into the sun. If we move too fast, we get away. And so it's basic mechanics to show that the attraction must be the same force, the same acceleration as the outward acceleration by Earth movement. And so we can determine the mass of the sun, just from the movement of the Earth. Well, if you have this kind of galaxy clusters there, of course, yeah, that's harder, because there are many systems. But again, what I just explained there, in terms of attraction and outward acceleration, well, you can explain that in terms of potential energy and kinetic energy, and you find that typically the potential energy is twice the kinetic energy. And that also applies to this kind of large many-body systems. And already in the 1930s, an astronomer called Zwicky, in this cluster, determined the relative velocities of the galaxies, and he found that they were much too high with respect to the mass he saw in these galaxies. Conclusion, there is more mass in these galaxies than we see, dark matter. He called that dunkle materie in 1933. It remains fairly unknown until, well, we had this kind of measurements from clusters, where in the space age, we could see that between the galaxies and the clusters, you have very hot gas. And that is gas lost by the supernovae which escaped from the galaxies, but it seemed to be confined to the cluster. So it was gravitationally bound. And X-rays, where you see that, has a fantastic advantage. You can determine the hot temperature from the spectrum, but also, because X-rays go through everything, if you see more light in the center, it's because there is more matter in this color. So you can really see measure the density, the temperature, so the pressure which oppose the gravity, so you can determine the gravitation. And what do you find? Zwicky's mass. Well, 5 times more mass. And then the rotation curves of galaxies is another argument. So it seems that there is 5 times more mass in the galaxies than we can see. And that means it does not interact with light. It does not emit light. So it is not electromagnetic. But it can also not undergo the strong nuclear interaction, because in that case that would have altered the chemistry in the early universe, and the previous result would not fit anymore. So it should just, yes, besides gravity, it should act through this other, more weak interaction, but no clue has been found yet. So we don't know what it is. And then there is the dark energy, and here I am at Lemaître's paper, which was done in the early 30s, translated into monthly notices, but he published in the Publication de la Société Scientifique de Bruxelles. Annales? No? Annales de la Société. Yeah. I mean, I have been at this university president of the professors. Excuse me, Mr. Chairman, that I am again on another path, but it is so that people can rest a bit. And, well, at that time, the procedures were started to evaluate the professor. You know that professors are not very happy about that. And I wrote a paper in the following, I said, well, who is the most famous, most respected, most remarkable professor we have had here in Leuven in the 20th century, Georges Lemaître. And I said, well, we as professors, we have to do 3 things. three different kinds of actions: teaching, research, and service to the community. So I said, well, his teaching, well, you don't oppose if I say his teaching was not terrible, eh? No. Yeah. But he had very good students at the end, eh? Because they were curious, what is behind there, and they worked on this. Second, his research. Well, how do you measure the quality of research? The impact of the papers. It was le bulletin, les annales de la Société Scientifique de Bruxelles. And third, I apologize to the Dean of Theology, his service to the community. So he was president for science, he was a founding member and president of the Pontifical Academy of Sciences, but I said in my paper, being appreciated in Rome is not so positively viewed here in Leuven. I got very good reactions from all my colleagues who said, yeah, you're right. Here you have his paper, and this paper is very clear. His papers were extremely clearly written. Eh? Yeah, and there with the 40 nebula and Hubble's list, you have that. And then you see that indeed you have a fast expansion and then going up. And he needed that because the age of the universe was not fully compatible with the expansion time scale, but the people realized that the distances were wrong. But in fact, in the 1990s, the same problem arose again. Because, well, we have, it was a discussion between theoretical physicists and astronomers. From understanding, well, from understanding, from trying to understand the first second, you find very interesting basic physics in the sense that you can do some prediction on the universe, and because you have some, well, the universe should have a certain density in order to beat as we see it today. But with this larger density, the age of the universe, again from the Hubble timescale, would not fit. The universe would be some 10 billion years old. And we astronomers said, this is impossible, the globular clusters are older than that. And so, well, we astronomers said, these theoretical people with their fuzzy theories, I mean, they are impossible. They thought these astronomers, well, that's qualitative science, they do not know about exact results and so forth. And then astronomers tried to measure that and to measure the real density of the universe, and they found that, in fact, it could be only reproduced with an additional term, which is this dark energy, which is exactly the one, the cosmological constant which is there, but on a different scale. What is the advance we could make? Well, the original Hubble diagram, also for Lemaître, is this part here. Yeah? This part. Now, with our present distance measurements, we can go much, much farther up. And then that means that we can see the expansion not anymore close to today, but before yesterday, billion years ago. And without this kind of acceleration, so that after the coffee break, you start again. Without this accelerating term, you have the straight line there. And with this accelerating term, you fit the data much better. Yeah, you're not sure you are so much convinced, but also through other measurements, this is confirmed. And okay, that works as dark energy. That's fantastic. So we have everything. Well, we understand the universe is normal matter, which we understand very well, dark matter and dark energy. But the normal matter we understand is 5%. The 95 other percent we have no clue. So that's not exactly to be happy about. And then, well, that is something I don't know, because I want to do the other part of the talk as well, of course. Well, we talked back, we discussed back this background radiation. I showed you it is homogeneous, the same in all directions. So it's the universe itself which radiates in this region. But yeah, it's the same in all directions. But do you know something which is absolutely perfect? It should not be perfect. And in fact, it should certainly not be perfect, because if you, I can understand that in the first 400,000 years, when the matter is charged and you have radiation all around, that you will not form galaxies through gravitational collapse. But once matter, radiation and matter are decoupled, because the matter becomes neutral and the radiation cannot influence it anymore, then gravitation should be able to collapse regions which somewhat higher density than the rest. But you should find this small fluctuations. Now, where? In the background. Because where you have, after this 400,000 years, you have regions where there is somewhat higher density. Well, that was also before the 400,000 years, and then they were in equilibrium with the radiation. So the radiation would also have been somewhat denser. And after 400,000 years, the radiation did nothing else than expand. So these kind of fluctuations in the background radiation should be frozen in. And we should see them today. I mean, this is marvelous for a theoretician. Gravitational instability is fairly easy to parameterize. But yeah, you have equations, but the result of an equation determines on the starting conditions where they start to apply. It's there. You can see it from the background. So you may know that a few years ago, Jim Peebles got the Nobel Prize. Jim Peebles, one of the Lemaître laureates in Louvain-la-Neuve. The Nobel Prize on the helium abundance, which we discussed, but also on the prediction of the with silk, on the then later fluctuations of the background radiation. And then these models lead to this kind of filamentary early universe, which is not unlike what we see in the data. And so we can model structure formation, and people are fairly enthusiastic about, but there are some problems which remain. And then that is the final one, and then I turn to religion, if you feel still motivated. Yeah. Well, we see, so we can look back. And the farther we can look back already quite far in time. And that is, as I said, galaxies should evolve. They should have been born and then grown up and then get old. Okay. And so, well, the universe is expanding. The farther you go, the farther they are. The faster they recede from us. So the more the light is moved into the infrared. So the Hubble Space Telescope has discovered quite some very red galaxies very far from us. And then you have this kind of diagram there that gives us typically the brightness of a galaxy, intrinsic brightness of a galaxy, backwards in time. The left is today. If we go backwards, and the look back time, 10 billion years ago, we were at the maximum. That was really the Sturm und Drang periods in the universe. And you see at the logarithmic scale, there was about 10 times as many stars formed and 10 times as many light. Really, we are getting old. We're a galaxy, we have 10 times less. But that's okay. Because if we look in our own galaxy, we see that the stars without heavy elements, well, stars which are born, let's say about 1 or 2 billion years after the galaxy was formed, have already half as many heavy elements as stars today. So it means that half of the heavy elements were made in the first 10% of the time scale. That means, indeed, that the galaxy must have been brighter. And that is, of course, the reason where Hubble was so wonderful. Where Hubble could see so far, we would never have believe that Hubble could be so far. But of course, because the farther you see, the more diluted the light is, because if something is, a candle is at a larger distance, you see it like that. But on the other hand, they are brighter. So it's because they are so bright that we could see so far. But at a certain moment, they have to start their evolution. And that is the right part there, and then we have much less. Because not only they are still farther, so less lights, when light is more spread out, but second, they are fainter. They are not in Sturm und Drang, they are still children. And that is where here we have James Webb. James Webb telescope was made in order to do this. Good. That's all the problem. So you see, we are advancing, but then I come to the more philosophical part of it. I should not venture in there, but I did some philosophy. Yes, I did some. I got a special program in philosophy, and well, I will discuss that. Yeah, here, what I learned there. Well, look. Well, for me, we study the universe, but from inside. And we are part of the universe. It's even more. We are a product of the universe. And that means, in my opinion, elementary logic is that the final word we never will be able to say. And so, well, we are rather comfortable with, well, are these questions? Not necessarily. And, well, one of the things I learned in philosophy, that was the philosophy of language. I, as a naive beta scientist, I thought, well, the language, that is just the tool where I express my concept. But then since I have had children and grandchildren and see that the conceptual possibilities increase tremendously by learning words and speaking a language. So the concepts we use are also born in there, and so we to some extent speak the language which the universe tells us to speak. So again, we cannot really tell the last word. So space and time, okay. Well, what was there before the Big Bang? Well, then I always answer, well, be on the northward of the North Pole. Is it cold or warm? And then they say, oh, if you go more north still, it must be colder still. But there is no north of the North Pole. Okay, a little bit the same. So you have to realize that. And then I put there Newton and Einstein. Well, on the relativity of space and Einstein, there Einstein really made a big advance. For Newton, there was absolute space and in a sense, filled with galaxies and an absolute time. And people feel that is more comfortable, but on the other hand, I mean, if the universe had been there since always, then it is a tremendous coincidence that we are here. Why, if there is no development, if there is the same universe always, why should we live now? I mean, this is very strange. And then also Plato and Aristotle. That is the other thing I learned from Herman Roelands. Well, we spent half of the course to Aristotle. And I also, well, I was rather Platonic in the sense, well, you have the allegory of the cave, and well, our universe, no, what we see is a kind of just projection of more abstract entities. When Aristotle said, well, be serious, calm. So, well, start with experiment and with empirical things you can, but of course, making concepts is interesting, but you should not exaggerate. I've often said, well, if Aristotle's worldview is subject to some corrections and has been, but if he would have knocked at my door in a certain moment and say, well, I want to do a PhD with you, I would immediately have given him I would use all my spare money to pay a grant for him. If Plato had come, I would say, well, go 2 stores higher to the theoretical physicist. Okay, good. So, and then, At the end, we may ask ourselves, why do we know anything at all? Huh? Because the wonder is not that we will not understand the last words, how brilliant we are. The fantastic thing is that we are able to understand something. And there are two important arguments there. That's first, the laws of physics are universal. That seems strange that we say that. So I am a physicist, so our laws should be obeyed by everybody. That's not the logic behind. Because the laws of physics are not voted in any parliament. They are discovered through experiment. And they apply, yes, well, in Aristotle's time, everything was below the moon was different than what was beyond. And now it's Newton who really, with his apple and the moon there, who changed that, who realized, no, what makes an apple fall, or what binds the moon to the earth is the same force of gravitation, and it also helps us to explain why how the planets turn around the sun. If we see a star, the third giant of physics, Maxwell. Since 19th century in Maxwell, we know that light is an electromagnetic wave. If we see the waves, I will say how romantic astronomy is really, observing the stars. I look outside and I see Orion there. I say, oh, wonderful. Because I know what light is. So it's an electromagnetic signal which falls on my eye and is then focused, and then with a small wire brought into my brain, and then a picture is made. So if I see Orion, I say, wonderful, Maxwell's law applied there. Can you think of something more romantic than that? Okay, so that's point one. And second is, what I said already, on a large scale, the universe is very simple. The kind of, well, you have different kinds of galaxies maybe, but in sufficiently large fractions of the universe, you have the same amount of galaxies everywhere. And then, as I said, the gravitational force is the only force we have to take into account. So it's very simple to do this cosmology. But of course, if then you feel that find that there is dark matter, dark energy, and that your early galaxies, you are not really able to understand them very well, you get into trouble. But that we know so much has to do with the fact that it's very simple. And that's in fact, if you ask me why I have become an astronomer and not a biologist, it's because astronomy is so much simpler. Okay, good. And then, let's go back to Lemaître again. And that is something he said in the 50s. As far as I see, well, it's also a little bit, it's what he said on the movie which was recently recovered in the archives of the television, an interview with him in the late 1950s, and here it is taken at the Solvay conference. As far as I see, such a theory of the primeval atom remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being. He may keep, for the bottom of space-time, the same attitude of mind he has been able to adopt for events occurring in non-singular places in space-time. Well, that's maybe a more technical issue. For the believer, it removes any attempt to familiarity with God, as were Laplace's chicanode or Jean's finger. It's consonant with the wording of Isaiah, speaking of the hidden God, hidden even in the beginning of the universe. Science has not to surrender in face of the universe, and when Pascal tries to infer the existence of God from the supposed infinitude of nature, we may think that he's looking in the wrong direction. It's very polite, but it's as he said it. But then, Laplace's chicanode. I would like to say a few words on this one as well. That's the chicanode, that is, Laplace is apparently we will see what happens. In fact, because Laplace is seen as the villain here, but you theologians, you should make a statue for him. How did the question arise? And Newton had indeed discovered the law of gravitation and was able to very well describe how planets move in ellipses. But the problem becomes tricky from the moment you have two planets at the same time, which also influence each other. Huh? In our solar system, Jupiter is an important planet in mass and influences and perturbs the motion of the others. And the problem is, in simple analytic mathematical ways, not solvable. You need numerical work. And then the solution, well, the problem arises, if you get a little bit disturbed, because, well, could Jupiter not at the end chase us out of the solar system? Huh? Is the solar system stable? And then Newton, he used, well, in fact, unbelievable for such a, I think, such a bright person. He said, well, if well, he was a deist, and that was the chic node, in fact. If the problem gets a little bit out of equilibrium, then the unmoved mover will do a small correction, and there you go again. And that is, he called the chic node of Laplace, it is in fact the chic node of Newton. And then later on, Lagrange and Laplace developed this perturbation theory, and they compute numerically the evolution of the solar system over a time scale of about 6,000 years. The biblical time scale of the universe. And they find that it is okay. And Laplace presents his paper at the Académie des Sciences in Paris, and Napoleon was there. Well, okay, in our academy the prime minister never comes, but Napoleon was there, and he asked, et Dieu dans tout cela? Laplace answers, sire, je n'ai pas besoin de cette hypothèse. And because he said that, he is really, to some extent, blamed as being the materialist who denies that God can exist, because you don't need him for explaining the physical world. But in fact, he should deserve to be honored, because, I mean, he has helped us to abolish a stupid theology. That's not Newton. I mean, a God God, he's the timekeeper and the concierge, who you say that, the housekeeper, who in the morning opens the doors and puts the heating on, and in the evening put the heating off, and goes around the house in order to see whether all lights are turned off and where the windows have been closed. I don't think that is the biblical God. Huh? Good. But interesting, today Laplace computations have been repeated for the 4.5 billion years. Not for 6,000 years, but numerically with computers you can do it. And it's okay. We will never be able to be mathematically that the solar system is stable. And there is one planet which is at risk to a certain moment, do strange things, that Mercury, which is close to the sun and which has a high eccentricity, and so it's perturbed, and it's the smallest mass, and the smaller the mass, more easily you can perturb it. But stability seems to prevail. But since we have discovered a lot of other planetary systems where we see that the stability is not generally true. And now that is the other aspect here of modern astronomy, which also to some extent appeals to philosophical, nearly religious argumentation, in the sense, are we alone in the universe? Huh? Okay, that is, in fact, if we are alone in the universe, I mean, that is, to some extent, this question is also in the background of the problem of Galileo. Because if the Earth is revolving around the Sun, rather than the reverse, we should see the movement of the Earth, we are moving, reflected into the stars. We don't see them. It means that the stars are very far from us, said Copernicus. And that is not exactly, well, then it makes that the universe is very big for us. Why? It's not very logical. That was a worldview which was new. And then we would say that, okay, there are so many stars now, and so all must have planets, and in all of them there must be life. Yeah, okay. Now we are trying to discover the parameter space, and we see that the planetary systems are extremely diverse, which doesn't mean that nothing like ours exists elsewhere, which also doesn't mean that on other planets also complex chemistry can take place, but we see that the world is much more complex than what we have in our solar system. We thought at a certain moment that all solar system would be modeled for all of them. It's not true. Huh? So, and there we are again in a new discovery space, which is huge. Huh? But then on the other hand, geophysicists learn more about the history of life on Earth. And there we are telling that there are many planets, but we are also learning that there are a lot of very, very strange things that has happened on our planet. So to discuss the probability of life elsewhere in the universe, it's in mathematical terms a kind of limit, infinity times zero. Infinity, many stars, zero, very unlikely that something so interesting as here happens. So it has taken 2 billion years before we had multicellular life forms. Okay, and then, the result depends on how infinite is infinite and how zero is zero. Yeah, and we are exploring how infinite is, but we are not yet there. But again, we are moving closer and finding something. And maybe the right answer will be, there may be a lot of planets, but on the other hand, the amount of planets which are in our vicinity so that we really can see evolved life forms on them may be very small. So the answer to the question, are we alone? Maybe. They are alone as well. Yeah, okay. Good. So we come back to, will we know everything? Well, so you have already heard my answer? No. On the other hand, so the beginning of the mechanicist view, as Simon Stephen has said, wonder is geen wonder. Wonder is not a wonder, we can explain things. And a lot of things which were accepted as wonder make sense, but on the end, so we understand how the galaxies form, but then we have new problems and so forth, and go on. And every solution arises new questions. In my opinion, there are two philosophers of very high importance in the Dutch-speaking world, and that is Johan Cruyff, with elk nadeel heb zijn voordeel, I don't know if you know. And the other one is Boudewijn de Groot, who has a very nice song. Achter iedere deur die jij open doet, doe jij een andere deur weer dicht. En toch blijf jij verborgen, nooit wordt er meer dan een tip van de sluier opgelicht. After every door, behind every door which we open, there is a room, but at the end another door and then another door, and that is exactly what we are experiencing. So, the Council has defined, Vatican Council has defined the Church as God's people underway. Well, we are also underway to understand better the universe, but, it will never end. We will always have new questions. Well, of course, at a certain moment. But I'm happy to have lived this time, because we have been experiencing a lot of advances in our technological possibilities, but from the moment that our accelerators have reached their limit, there we are. But bright people can do. So, and in this, natural science explains how things are, but at the end, we always end with questions why they are. And, that doesn't mean that there is no proof, physical proof that means that there is a big designer behind, but it doesn't at all make impossible that, there can be meaning, and that's not stupid to say. But science does not explicitly point at it, and I think that is essentially what Lemaître also tried to convey. So there are two unexhaustible mysteries. So I said there, God exists is a meaningful affirmation, but I must say, who is God? And what is exist? Huh? I am in great distress about, well, not distress, because these are fantastic questions, but I cannot claim to have the final answer to that. And in this, I see a paradox. Well, it's the same is true for physics. Our worldview has changed tremendously since ancient times. And, well, nobody has ever doubted that the world exists. So if our views about God turn out to be incomplete, culturally biased, and so forth, we have to adapt ourselves in a new culture and ask the same questions in a more evolved way. But many people would say, oh, you're wrong, so that's a proof that God doesn't exist. I find that a little paradoxical. But then, well, I am not a theologian, and I should not venture in things I do not know. Yeah. But let me say a few words about the question, because often, and that's certainly true in the Anglo-Saxon literature, the fact that the Bible starts with, in the beginning, God created the heavens and the earth, means that, in fact, the religious question is an answer to the cosmological issues, to the cosmological problem. In fact, people always say the Bible is not a scientific paper. It's not. It's not about science. That's one thing. But if you, on the other hand, look at the 5 first books of that's my own feeling. The 5 first books of the Bible, the Torah, or the Pentateuch, whatever, the construction is a little bit like a scientific paper. You have an introduction, you have a core chapter, and then you have a discussion and conclusions. And what is the core chapter, which has been written in the first? And I must confess, I have written a certain number of papers, and I don't think there is any one paper where I started writing the introduction. You do that at the end. And what is the big finding? Monotheism. And they may have learned it in ballingschap, what is that? Exile in Mesopotamia. Apparently it originated around Nineveh somewhere, whatever. And okay, but then, there is a big discovery. Well, all these multiple gods do not exist. There is one God, and He cares about us to some extent. And then, and then you have the introduction, because if it is so overwhelming that everything must be, that it changes our view on everything, and so also the world must be born like that. And on the other hand, it tells us that we should wash our hands when we eat, and then, not eat swine, pork, if it's too hot and so forth. Well, I don't know. The conclusions, the new paradigm. But, well, Genesis 1 is by no means intended for cosmology, and it's Mark Vervenne who told me, and also I think it's in one of the lectures we had, one of the last weeks also, I think it is in Exodus or in Deuteronomy, I don't remember. It's also marked. The earth was, the heavens were created, the world was created in 7 days, and the 7th day you have to respect the Sabbath. So it was the first social pamphlet in history, that the Jews in exile, they had to work 7 days per 7, and that was too hard, and they said, well, we need a 7th day to rest and to really to be concerned with the essential things of life. And then that is exactly what Genesis did. But on the other hand, Genesis 3, I think is wonderful. That is, well, we have already had the apple of Newton, there's another apple here. Yeah? And what is it? It is the story of the man who lives in paradise, does realize, does not be happy enough to live in paradise, but at the end wants to be God himself. And, well, some scientists should read that rather than Genesis 1. And so they have found something, and that is, it becomes central to every explanation of the world, and they are the new gods themselves. Yeah. Okay. I will not mention examples. You can think of some. So, and also in this Old Testament, well, there are different views on God. I mean, well, I have there Joshua 6:1-27. That is when they blow on their trumpet and the walls of Jericho fall down. Well, I must say that is a God view where I am not very familiar with. On the other hand, you have, well, we have had another apple. Now we have another cave. Elijah in the cave, where, well, he has an appointment with God, and, well, he waits. Well, he will give a sign, and there is a, what is it? I don't know the order, but there is a big earthquake. No, it's not that. There's a big storm and a fire. And each time Elijah says, no, that's not exactly the God who I'm waiting for. And then there is a small breeze and say, oh, sir, and let's talk to each other. That I like. And then in more recent, well, because I haven't talked about the New Testament, but in my opinion, the real Genesis, the real well, text, if you wish, in the Bible, trying to relate science and religion is a little bit. And at the beginning of the John Evangel, what is it? A Gospel. In arche en hologos, kai hologos en proston theo, kai hologos en theos. So the meaning was there from the beginning. There was logos. Oh, we have a nice story to tell about logos. People ask, well, sometimes I give a talk, and then the people present me as professor of astrology. Yeah. And then you have to be angry. You have to. Well, really? These people are right. Well, I mean, good. Well, logos is about understanding. Nomos is about law. Just coincidence. And yeah. So the real science is logos. Psychology, biology, geology, and so forth. And we are theology. There you go. And we are astronomy. The reason is that the real name of our science has been taken up by a group of charlatans. So we should exchange, and you cannot blame people who call us astrology because they understand logos more than nomos. So I once was invited for a discussion with an astrologer, and it was organized by whom? Well, by the committee, well, or the organization of the Italian people working at the European Union here in Brussels. So they had their regular meeting, and then they wanted to have the final discussion about astronomy versus astrology. And normally people always say you will lose, but I was happy to have a very good opponent. Well, I mean, he was very clever. I mean, he tried to explain the behavior of Bart de Wever from his birthday. Can you imagine? Of course, people were totally lost. And I explained them, and I in fact asked these people, let us have a vote. Shall we exchange names? And I won. By a large margin, but it hasn't happened, because, well, you earn more with the stupidity of people than with their intelligence. So there you go. But logos, logos, meaning, well, looking for consonants and so forth. And then reality and meaning, okay, but I would say in the New Testament, my last sentence here, which I wrote at the end still, I mean, if I believe it's because I'm really, I'm amazed and by the personality and wording of what Christ has been and has said. So, and well, I think that is more important, but he has been absolutely silent about cosmology, just like Father Damien. that was not really what he needed, so I could not really find an interesting sentence of Christ to mention here, unless maybe give to the emperor what is in his competence and give to God what is in his competence. And then to come back to Lemaître, well, that is something I do not have the source. My former director, Professor Smeyers, who will be 90 years old soon, he once told me he had attended a conference about science and faith by Lemaître, and I think it was in Namur. And there Lemaître had well, I have never seen it written down, but apparently he had a kind of comparison with the typewriter. And he said, well, the cosmos is like a typewriter, and we cosmologists, we can really understand and try to understand the mechanisms of the machine. But we have no clue on the letters which are written there. I like this one. I like this one. And in then the famous recording of Lemaître's interview in the late 50s, about that he said, at a certain moment he said, I have recently talked about that in a conference in Namur, and that has been recorded by RTBF or so. And well, I asked Thomas Hertog, do you know about that? And they haven't found it. But well, hopefully that could be something which we could look for. And I think I'm close to the end. Yeah? Yeah. Look at, is there more still? No, that was so to conclude, we know always more. We know already a lot more than in Lemaître's time, as well observationally as theoretically, it evolved. But we remain as unclear about our status, if you wish, within the universe. And the more we know, the larger the mystery becomes. So, to answer Simon's statement, wonder is toch more. And religion and science each have their place and their language, but there is no reason to get schizophrenic whatsoever. And then, in fact, the last word, people think about the debate between science and religion as something very new. But read again in the Actas Apostolorum, chapter 14 or 17 something, Paul on the Areopagus, when he is in Athens, and well, he looks around in the town and he sees, well, a temple and an altar for an unknown god. How can clever people have such crazy ideas about God? So he said, I will tell you who God is. And he goes down, and a lot of people come, and he convinces some of them, others not. And at the end they say, well, I mean, about this resurrection of Christ, we would like to hear you again and a few things, but come back, we will continue the discussion. And if you in fact read that, you say, well, the debate is exactly the same as today. So probably tomorrow it will still be the same debate. And yes, there is my epilog. I mentioned something about exoplanets, and well, you know this picture, Christmas 1968. And well, the beginning of manned spaceflight, and then in July '69, man was on the moon, and that was great. And I remember time then that people said, well, von Braun said in 10 years we have colonized Mars. And a lot of optimism generated that we would really now explore the universe. Well, what is the biggest discovery of manned spaceflight? We astronomers do unmanned spaceflight, and we find wonders in the universe, but what has manned spaceflight discovered? Also a wonder, planet Earth. That is the big discovery of space. If you ask Frank de Winne what he's doing when he has what he was doing when he has some free time in the space shuttle, or sorry, in the ISS, looking down, he said, yeah, and well, and we have learned how fragile it is, and that we have to care about them. Well, are we all convinced? I hope so, but here maybe, but we're still a long way to go. Okay, and that's the big discovery. Well, to some extent, I see today in these discussions, which I am a bit part of the life in the universe, people say, oh, it is obvious that there must be life everywhere, and we will soon find it. Well, I'm not so sure, but what I hope is that in 50 years from now, we will, a little bit as what we have experienced with planet Earth, we will be in a situation that we finally understand, thanks to the comparison of all this diversity of worlds everywhere, how remarkable and wonderful our life here on this place is, and that we have to cherish it and not kill each other. Okay, that is my conclusion, and I thank you very much for your attention.
Thank you very much, Professor Waelkens, for allowing us to participate in your curiosity and your wonder in this wonderful lecture. It was very lively and it was very fascinating. I think we kind of lost track of time, and so we are very grateful for, I would say, bringing the expanding universe closer to us. I would like now to call upon the director of the college to express the thanks of our community.
Ladies and gentlemen, Professor Waelkens, thank you very much. It was really a marvelous evening for all of us. We would like to thank you. We have a small gift for you. It will be very small chocolate items, which I'm sure you will be able to use in family circle the coming days already. Thank you very, very much, because really this is another stone in our Lemaître lecture path. So we're really happy to have you at this event. Thank you. Great. Ik wil naastgeven dat er aan de binnenkant zit. Ja.
To conclude, I would also like to thank Professor Verwenne again for the recording in which he introduced us into the topic, and I think prepared very well for the lecture of Professor Waelkens. Last not least, I would like to thank all of you and express our deep gratitude for being here and by your presence making the continuation of this annual lecture series possible. Thank you very much, and hope to see you soon.